we talked, I did send out an email to let everybody know that you're allowed to do a self-proctoring. Of course, you might not have access to be able to use internet and a actual camera, video camera. But if you have access, if you have a webcam, and possibly you might need a mirror. But if you have a separate webcam that's not mounted to your monitor, you can do it without a mirror. But if you have that, then you could actually just self-proctor as long as you follow the instructions in that email. So that's still an option for you, but I'm still going to send him the Proctor application, and I'll send that immediately tonight.
Yeah, I'm on the ship, so that's not. I've done it that way before. I had Mr. Kirby earlier for pre-calc
Right.
a few semesters back, and
Right.
that's what he did, the double camera where you put the camera to the side and you put the camera in front of
Right.
you. But right this minute, I wouldn't be able to do something like that. If it was next semester, I should be back.
Yeah,
But
I was on the
yeah,
bush. I know, I know things don't work quite as nicely when you're out to sea. Uh, even though I was only in the bush for like 16 hours, but I was far enough out to sea to know that it was not a convenient area to get internet and all that good stuff.
absolutely not. And then if let's say you're using an online, and you don't have to use it and you go into River City, now you just lost your test. Now you get to email your professor and ask for, help.
Yeah, yeah, it's no problem. I'll take care of it. And like I said, anything that happens that's on me. We'll deal with that because obviously he sent me a text message back on Saturday and I didn't respond till now. So if anything gets delayed, that's all on me. I'll take care of it and I'll you won't be losing any points because of my screw up.
Thank you, professor. I appreciate your time. Thank you.
You're welcome. I'm looking at somebody just sent me a text. The in-person lab today was available to take face-to-faces. Yes, awesome. That's great. Beth was just saying the in-person lab today was available to take the face-to-face test with a question mark. Yes, that was absolutely what we had mentioned. I took the test on the lockdown browser with the lab instructor as a proctor and wanted to make sure. Yeah, absolutely, that's valid. Thank you very much. I appreciate it. Uh, I also took the password off for anyone that used it with an actual camera. So that was on purpose because if you're actually using a webcam and the respondent's lockdown browser, then you're actually eligible for all of that. So you can take it without having to have a actual proctor there. I've done something with my Zoom window. I don't. Oh, there he is. Whew. The new Zoom's got all these bells and whistles, and I just hit something and I lost all my students. I didn't know who was there anymore or anything. Well, that was scary. Okay, but I found it now. It don't have a little square or anything up in the corner that says, "Hey, this is to minimize or maximize your window." It just disappeared all of a sudden. So, all right. Well, it is time to start. Does anyone else have any questions before we get started? This is a good time if you have any, for instance, projectile motion equation questions. I know, Adrian, by the way, I know you sent me a problem and I told you I'd get back with you. I plan on doing that right after class. I would have done it last night. I would have done it today, but all heck broke loose in my personal life here. So I've driven about 380 miles in the last in the last 12 hours. So it's been a nightmare. That's why I'm a little behind. So I apologize for that, but I will get back to you, or we can just talk about it at the end of class if you want. So, anybody have any questions? Anything bothered you about the vector stuff or about the projectile motion stuff? I did want to remind everybody that test one does include like the concepts, a couple of simple concept questions regarding projectile motion. But other than that, it's just vector addition stuff from chapter three. Everything else is just chapter one and two. But chapter three, remember, we only covered vectors. And I told you you'd only have vectors and possibly some conceptual questions about projectile motion. I'm not having you solve any projectile motion problems, but you might be asked, a couple, 2 or 3 points worth of questions on each question, just things about the projectile motion. So hopefully you'll look back over that before you take it, or hopefully you already took it and made an A. So that's even better. All right, so it does look like we don't have any questions. It does look like we have a pretty good number of students here. So what I will tell you is I'm surprised we didn't have any questions on projectile motion. I did show you two monumentally big projectile motion problems. And once you do see those and understand them, I don't feel there's much difficulty in doing any other type of projectile motion problem, other than occasionally you might have to do some tough algebra, like you're going to have to possibly use the Pythagorean, or excuse me, use the quadratic formula. That's very normal in the calculus-based physics class. Uh, you shouldn't have to do any derivatives or integrals, but sometimes you can. Like I showed you, one of the ways you could find the max height was take the y as a function of t and realize that the max height is in fact a maxima of the equation y of t, or of the function y of t. So if you want to find a maxima, of course, what you do is you take the derivative of it with respect to t, set that equal to 0. Then you plug that time in at t, that time t in to the y of t equation, and that gives you the actual height at that time, and therefore you know that's the max height. That's one of the ways you can solve it, but you could have completely solved that just by realizing, oh, well, if uh, if the position vertically as a function of time is negative 1/2 gt squared plus v0 t sine theta, then clearly the actual velocity in the y direction as a function of time is v0 sine theta minus excuse me, minus gt. And if you think about it that way, you say, well, I realize that an object has a vertical component of velocity when it's a projectile, but it has an upward velocity component while it's trying to climb to its max height. And then when it gets to the max height, the y component of velocity is 0, and then afterwards it goes to a negative. So if you just set the y component of velocity equal to 0, that'll give you the time at which the max height was reached. And then you plug that in for y, just like you did before, and that'll give you the max height again. So there's ways you can do it without integrals and without differentials or derivatives, but you can, of course, use them as well. So hopefully that was enough of an introduction to projectile motion. But again, you have a ton of projectile motion problems at your disposal. All you have to do is click on some of the links that I put in your Canvas page, or go straight to my YouTube channel and do a search for, projectile. So now that we've done all that, and I've sort of rehashed the issues about projectile motion, we're going to chapter 4. And chapter 4 is called Dynamics, Newton's Laws of Motion. So we're going to start off with an idea of what force is. And I'm going to try, I always like telling the history of this a little bit, but I've found that it takes up too much of the class time. Uh, and you can sort of get a good fraction of the history of it from reading. So I'll try to abbreviate it, but basically the short version is Galileo had faced the Inquisition. You can look up that Inquisition. You can even go to the Vatican website, and they actually have the transcripts of the trial and stuff like that. And they've even got them translated to various languages and stuff like that. Very interesting thing. But at the end of the day, he sort of got put in in-house arrest for a technicality. Uh, it wasn't completely as bad as you might have think, but it's still pretty bad what happened. The main thing is there was a cardinal who was a close personal friend of his, and the cardinal was the one that signed off on him writing this book, the Dialogues book. And in that dialogue book, basically it portrayed the position of the church by a person by the name of Simplicio, which means simpleton or a dummy or something like that. So that was a little damning. And in that intervening period between him getting permission to write the book and him actually publishing the book, that cardinal became the Pope. And he was a friend of Galileo's, as I said, but people started telling him, hey, this Galileo guy, he might be your friend, but he is definitely dissing us. So eventually the Inquisition comes along, and they did have to have a discussion with him. They put him on trial. There's many rumors about things that were said, but the main thing was he was ultimately sentenced, luckily, just to in-house arrest for the rest of his life. He was also sentenced to no longer study, promote, or teach anything about the heavens, more or less, about what would be called astronomy today. He was just forbidden to teach that. But he had enough information from what he had learned from making his own telescope. Remember, Galileo did not invent the telescope. That's a common misconception. He did read about someone, I think it might have been Rheticus, if I remember correctly. It's either Rheticus or no, there's another person who Leeuwenhoek, maybe. No, it wasn't Leeuwenhoek. Anyways, there was another person who actually did invent the telescope and wrote about it, and then Galileo read about it and made a better one and used that. And what Galileo did do that was original is he was among the first people to use the telescope to look at the sky. It turns out that Thomas Harriot, an actual physician and scientist of some sort on the mission to Roanoke Island, what's modern day Manio. He also had made a telescope about the same period of time and used it to look at the moon. Uh, but he was in the backwaters of podunk America at the time, which didn't really have a good communication system back and forth between Europe. So we didn't know, but evidently he was looking at it and maybe looking at the moon and the stars, maybe even before Galileo did. But again, this is just fairly recently did we figure that out that he had done that. So Galileo is sort of given credit as the first person to use a telescope to look at the sky. And when he did, he discovered, for instance, that Jupiter had four moons. He called them the Medicean moons. It's Io, Callista, Ganymede, and Io, Europa, Ganymede, and Callisto. Those are the four moons of Jupiter. And he had found those. And like I said, he named them the Medicean moons. We now call them the Galilean moons. But one of the key aspects of the whole idea of heliocentric universe was if the sun really was the center of the universe, then the Earth would be moving around it, of course. And their argument was that if the Earth was really moving like that, if a bird were to be sitting on a tree limb, for instance, on planet Earth and see a worm down on the ground, and he lifts himself off the tree limb to fly down to get the worm, soon as he left the tree limb, the Earth and the tree with it would fly by at hundreds and hundreds of miles per hour and leave him in the dust. That was one of the major complaints about the idea that the Earth orbiting the sun could be real. They just didn't understand motion. Because of that, uh, in all the models of the universe, Jupiter was actually moving. So it was definitive that here is a case where there's four moons that stick with the planet Jupiter. And everybody agrees that Jupiter's moving, including Tycho Brahe, who had the craziest model of all. And with that in mind, you have a big glaring contradiction to the idea that the bird would be left behind. So Galileo used that as his sort of niche to study while he was in-house arrest, which again I would argue probably he got that light sentence because the cardinal had become a pope, and the cardinal who was his friend probably made the sentence a little less harsh than it could have been. But either way, he decided to study motion, and the motion he studied was specifically the motion of falling bodies. And what he realized is if you drop an object like this pen, you drop that, it's hard to tell at such a small period of time, is that pen being dropped and then it slowly speeds up to a higher and higher speed? And then does it get to some speed that's reminiscent of the mass of the thing? Or does it keep accelerating to whatever speed it's going to possibly reach in the time it has? Or does it take off at some fixed speed that's reminiscent of the weight of the pen? Aristotle had taught us that basically there were four elements: earth, wind, fire, and water. Five, if you count the quintessence, which is Mila Jovovich, or the heavens. Uh, I wouldn't say that Mila Jovovich is necessarily the heavens anymore, but she did play that in the movie. So, anyways, the big deal here is the four elements were a part of the science in a way that you might not have understood. So, for instance, we had a hierarchy of elements and things, and earth, wind, fire, and water tells us there is a earth, and anything that you would recognize as a tree or grass or dirt or stuff like that, that stuff is of earth. And then when you start to burn stuff, well, when you're burning stuff, that's obviously partly fire, but you're also burning stuff that might be partly earth. There's probably some water in, for instance, a tree. If you actually cut open a tree that is was living just 2 seconds earlier, you will find water in it. So you can find a lot of different things in the elements. But the main thing is each element has its special place. So, for instance, things that are made of earth has as their natural place the center of the earth. Water, which you can see sits on top of the land on the earth and therefore is appropriately called its place is on the surface of the earth. Air exists above the atmosphere, above the water, and above the land, but inside the atmosphere, which is not in outer space and therefore not in the heavens. So you had a natural place for air, which is above land or earth and is above water as well. And then you had fire, and fire was like the sun. So, in some sense, you could imagine fire being like the sun, having its place as being naturally above the air itself. So there was two types of motion. There was natural motion, and that's basically what happened whenever anything was allowed to move. It would try to go to its natural place. So if you had something made of earth, like this clearly wooden pencil that I'm holding in my hand, which is not red, but is in fact clearly the color of wood, if that pencil were to be released, because it is earth, it's going to obey the laws of natural motion and it's going to naturally move with no force whatsoever to its natural location, which is the center of the earth. And yes, they knew the earth was spherical at the time. So this thing would fall, and the reason why it falls is it's trying to naturally get to the center of the earth. Now, if you were to take this pin and it's sitting on a tabletop and you try to move it left or right, that's unnatural motion or violent motion, and you actually have to implement a force to do that. And that force has to be constant. Like you can't just push it and it's going to coast. No, you got to push it and keep pushing it. The coasting could possibly happen, but they had other ways of explaining that. So that was the way we saw motion working and stuff of that sort. Not only that, they said that objects fall at a rate proportional to their mass, so that an object that's 100 kilograms is going to fall pretty fast, but an object that's only 10 kilograms, that's going to fall about a tenth as slow. So in other words, it would go about a ten times slower than the 100 kilogram object. So that was the stuff that was being taught by since Aristotle, in fact, but by Aristotle and then everybody after then. And in the meantime, we had Emperor Constantine, who introduced Christianity to the Latin Roman world, if you will. And Emperor Constantine, of course, got basically the religion of Christianity to take over a large segment of the world. And by the time we get to Galileo, we have a huge church organization that has taken the time to thoroughly read all the scriptures, all the existing texts from before the Bible was actually codified in, roughly the 400s, the temple, the Council of Nicaea, and all that stuff. So there was so much stuff built into what we call physics at the time that it wasn't easy to just say, hey, well, I did an experiment and the laws of science and the way science works is that any experiment, if done well and repeatable, will automatically change the universe if it, proves something that we thought was true was not true. That is supposed to be the case, though they hadn't quite worked out all those details about what science was at the time. They were getting really close. But the big thing was because of this inertia it had as a result of being part of government and interpretation. I mean, literally all the scripture was interpreted in terms of Aristotle's teachings. So when you go saying stuff like things fall, or that the center of the universe is not the center of the earth, but rather the center of the sun. That's all got to be in terms of the Bible reinterpreted. So it's really problematic. So Galileo says, I want to study this motion. I need to get rid of these ideas of Aristotle. I can see things that are clearly not true about what Aristotle has been teaching. And, though I respect, Aristotle as a scientist, Galileo was kind of a snob and a cocky, arrogant butt. So he's going to behave exactly the way he wants to and try to plead his case no matter what. He's not going to just show deference for no good reason. Okay. Which is a good thing for science, but it also can lead to things like maybe you get burned at the stake or maybe you get hanged or something like that, which is suboptimal at best. So Galileo goes to his in-house arrest. As I said, he wants to understand motion, and he realizes that the time constraints for objects falling are so small that he doesn't really have a good clock type mechanism that could measure motion very well. So he has this brilliant idea. He says, well, yes, these things fall vertically at some rate, but if I use an inclined plane instead of dropping things vertically, then I would get an acceleration that he reasoned would be proportional to the vertical acceleration that things get. Even though I'm saying this as someone who knows that he's ultimately going to find out acceleration. Galileo didn't know he would necessarily discover acceleration or constant velocity or any of that kind of stuff. He just knew that to study the motion, he needed to slow it down. And he reasoned that basically understanding trigonometry would allow you to get back from the acceleration down an inclined plane to get back to what the vertical acceleration would be. So that's what he studied. So first thing he realized was when you allow an object to slide down an inclined plane, it increased speed. If you take a rolling body, say, and allow it to roll up an inclined plane, I think I said it reduces speed just now. And if I did, that was wrong. So if an object is rolling or sliding down an inclined plane, the speed increases. I do think I said decreases because I was planning on doing the other way first. But anyways, so yeah, when an object goes down an incline, it speeds up. When an object goes up an incline, it slows down. So he argued just from logic that if ramping up causes it to slow down, ramping down causes it to speed up, then ramping level should be something where there's no change in speed. So that was his argument. Uh, he also went further than that in that he gave us a definition of speed and velocity. I say speed and velocity because vectors and vector calculus, vector algebra, all that stuff didn't come into fruition until the mid to late 1800s. So we actually invented vector algebra probably around the 1830s, and then vector calculus as well around the 1830s to 1860s. And it was mostly done by Oliver Heaviside and I believe it's Gibbs, Stephen Gibbs of Gibbs Free Energy that you've heard of from thermodynamics and chemistry and stuff like that. Those two guys independently, Gibbs in America and Oliver Heaviside in Great Britain, uh, co-discovered vector calculus basically, and uh, various transformations as well, Laplace transforms, stuff like that. They all invented that and discovered it, I should say. But that wasn't until the 1800s. So Galileo had no sense of vectors, nor did Newton, even though they probably had some idea that they had to have something bigger than just numbers because they understood object things like forces had magnitude and direction, and both of which were important. But since Galileo didn't have that, what he did have was just his good, brilliant brain and his ability to think of things and do experiments and his willingness to do experiments. Because in this time period, experiment is not an accepted method of discovering the way nature works. Aristotle basically said, here's this beautiful logic, and he's a great logician. And with this beautiful logic, you start on first principles, and those first principles are things that you don't have to prove. It's just obvious. But give it 200, 300 years, you might look back and say, well, those things that we thought were just obvious were not only not obvious, they were in fact completely wrong. For instance, some of the ideas that Aristotle had was since the heavens were the heavens, the quintessence was the heavens, then they are the heavens, and therefore, by definition, they have to be perfect. And the perfect shape is a sphere, or if you have to reduce it to two dimensions, it's a circle. So they would argue that everything has to move in a circle or a sphere in outer space. Again, no reason to prove that. That's just common sense to them, but clearly not necessarily common sense to us. Another one was the heavens are the heavens, which means they're immutable, means they don't change, they can't change. So when you see something like a planet speeding up, what you're doing is saying, oh, well, the planet was going the wrong speed, so it had to speed up to get to the perfect speed, which is the right speed, and therefore the only speed it should be. Or the planet was moving at exactly the right and perfect speed, and then all of a sudden it sped up to change it to a bastardized version of perfection, both of which are completely unacceptable. So, in addition to now having objects that only move in spheres or circles in outer space, they can't speed up or slow down either. So, all of these were baked into the science that we got by the time Galileo gets there. And Galileo's just not willing to take that. Galileo's willing to do experiments and find out. Uh, People from Aristotle's time and the Pythagoreans and these type of people sort of saw your mental capacity to think of things and to imagine things as the gold standard. So, for instance, why would you actually study a desk, for instance, when the idea of a desk is much better? You can take the idea of of a desk, and that idea will last forever. If you actually take a desk and put it in a room, 100 years later, it's going to be nothing but sawdust, probably. Well, maybe not 100 years, maybe 500 years. But the main thing is things degrade in reality. So the idea of experimenting with the Pythagoreans and then later the Aristotelians and stuff like that was not really that uh, palatable for them. They just didn't like the idea of doing experiments because this version, this universe that we're in, is a bastardized version of the universe. The true universe is the quintessence, the heavens, and this is our funky little screwed up portion of it. Okay. So that's why they didn't do experiments. Galileo did. Now, Galileo did see that, or make an argument that any object moving along a level surface should always go at a fixed speed, but he wasn't convinced that that was necessarily true. So he wanted to try out more experiments. So what he did do, for instance, he just started letting objects slide or roll down an inclined plane and then hit a level surface and then roll or slide up another inclined plane. So it was sort of like a half pipe, like we're used to from skateboards and bikes and stuff like that in the X Games. He sort of set up a pattern like that. And what he realized with this half pipe was that when you drop a ball and allow it to start rolling or sliding down one half of the half pipe, it would speed up, speed up, speed up, and then it would reach the horizontal part and then reach the upward part, and it would start to slow down, slow down, slow down. But every time it came back up, it almost reached the same height that it had initially. And he could look closely and see that the ball rolling down the incline would skip and stutter and bounce and stuff like that, and he knew that had some effect on it. So he went back and decided to like really sand and smooth out all the surfaces, polish them really well. And then he saw that, in fact, when you drop an object on an inclined plane, it would go down it and then try to approach the same height on the other side. But now that he did this polishing and sanding, it came even closer. And he'd do some more and it'd come even closer still. So he reasoned that if he could get rid of all those extraneous little forces, then he would actually experience exactly what nature's trying to tell him. And that is basically when you drop an object on a half pipe, that its natural tendency is to reach the exact same height that it was dropped from. So if you drop it from 8 foot high, it's going to go down the half pipe and then reach 8 foot high on the other side. So in this sense, he's using imagination to figure out what's going on. He's using logic and reasoning to figure out what's going on. And then he's also imagining further to things he can't actually physically do. Like he can't make a universe where there's no forces acting on a ball on a half pipe. So he imagines that such a thing could exist. And if it did exist, he can make a conclusion about it. And what he came up with was what we would call Galileo's law of inertia. And what he was saying was it's as if objects have some quantity called inertia, which is the reluctance to change their motion. the word inertia doesn't really solve any problems. It just sort of gives you a word that you can stick in there that make you feel a little bit better about smacking Aristotle in the head for the dumb conclusions he reached. That's about all it is. It's not really helpful unless you figure out what the inertia is or how it works or whatever. So that's what he went with, is what we call a law of inertia. And basically, what he said was it's as if an object has an inertia, a reluctance to change its motion, and therefore all objects will maintain constant motion unless acted upon by some other force. And what he meant by that constant motion is that they would go at a fixed speed in a fixed direction forever until they were affected by some forces acting on them. Okay. That later under Newton will become Newton's first law of motion, which says an object in motion tends to stay in that state of motion unless acted upon by a net external force. And that's partly what Newton said meant when he said, "If I have seen further than others, it's only because I stood on the shoulders of giants." That did show a little humility, and it paid a little homage to, for instance, Leonardo da Vinci, Galileo, various other minds that came before him, Aristotle, Galen, stuff like that. But it also was said in a room which was being monitored, managed, if you will, by one of his nemesis, Robert Hooke, who had an issue with his own stature. Specifically, he was not proud of his height, which seems to have been maybe 4'8", 4'10", something like that. So Robert Hooke was this short man that had what some people would call a short man complex. And what Newton's saying is, if I have seen further than others, it's because I stood on the shoulders of giants, not hobbits like you, Mr. Hook. And some other time, maybe we can talk about the fun of how those two got to be enemies or whatever. But the main thing is, I will tell you that Robert Hooke was a great scientist, and he did run the Royal Society, which of course you probably know today. Stephen Hawking was a member. Elon Musk is a member of the Royal Society. It's a very prestigious scientific organization, and Robert Hooke was the head of it. And Isaac Newton became the head of it when Robert Hooke stepped down. And oddly enough, they all had paintings done of them. And we have all those paintings except for one. One Robert Hooke's painting is missing. So that may or may not have been done by Newton. But the main thing that Galileo was able to do was get that law of inertia. And not only that, he came up with an idea of what speed was and what constant speed was. He said, an object in uniform motion, which meant a constant velocity or constant speed, is basically an object that travels the same distance in a given unit of time. So if you timed an object for, let's say, 8.4 seconds, and that just happened to be the standard that you did. So you measured time for 8.4 seconds, and you watched how far something went, and it turns out it went 8 meters in 8.4 seconds. So the velocity would be 8 meters divided by 8.4 seconds, so 0.96 something or something like that. Meters per second would be its velocity. But you didn't have to use the 8.4 seconds. You can use any unit of time, long as you consistently use that same unit of time. And when you find that unit of time that you're going to use, if you consistently get the same distance, it will be considered a constant or uniform motion, and therefore constant velocity or constant speed. He also went further to teach us what acceleration was. Acceleration is, in fact, constant acceleration is basically the motion exhibited by an object whose change in speed is the same for a given time interval. So, for instance, if you looked at an object falling and you discovered that its velocity changed by 0.98 meters every tenth of a second, then you could conclude the acceleration is 0.98 meters per second, and or excuse me, per point second, 0.1 second. So if an object has a change in velocity of 0.98 meters per second each tenth of a second, then its acceleration is 0.98 meters per second divided by zero point 0.1 seconds. And that gives you, of course, 9.8 meters per second every second. So that was something else that Galileo came up with. But now that we're there, we can now start using the terminology that we have for Newton's laws of motion. And that's really where we start, even though Galileo and Aristotle and all these people contributed. So I'm going to go ahead and share my iPad screen with you guys. I've now finished the uh, shortened, abbreviated historical portion, but hopefully I will read more about that. I would say in an astronomy textbook or stuff like that would be really nice, but you need not do it. The book has a decent explanation of the history, but not a huge one. So, all right, now I am in the process of sharing my screen. Hopefully, it'll pop up any second now. So your book opens up in chapter 4 with section 4.1. I'll go ahead and tell you that. In fact, the sections in chapter 4 are 4.1, which is force, 4.2, which is Newton's first law of motion, 4-3, which is mass, 4-4, which is Newton's second law of motion, 4-5, which is Newton's third law of motion, 4-6, which is weight, the force of gravity and the normal force. 4-7 is solving problems with Newton's laws, free body diagrams, and 4-8 is problem solving a general approach. And then it has, of course, two really nice chapter opening questions. So please answer those. As I said, the first section is called force. And what I want to tell you is what a force is. And I believe it was Galileo that first gave us the idea of using the word force to represent anything that could basically cause an acceleration. So that's one way of thinking about a force. A force is anything that could cause an acceleration. That's a little too advanced though, because y'all don't necessarily understand all the details of what acceleration is right now. So, for instance, like if I asked you, how many accelerators does your car have? You might not all realize that there's way more of them than you think. So, for instance, your accelerators in your car are, of course, the accelerator, which is the gas pedal. And it's called the accelerator because if you push down on it, it will cause the car to speed up. And in the normal language of everyday life, when we say accelerate, we mean speed up. But in reality, accelerate in physics can mean speeding up or slowing down or changing directions. That's the key thing to understand. Speeding up, slowing down, or changing directions, all of those are types of acceleration. Now that you have that, you'll realize, oh, okay, so the gas pedal is an accelerator, but so is the brake pedal. So is the emergency brake. So is the steering wheel. So is the clutch. So is the transmission. In some sense, the amount of gas in the car is an accelerator as well, because if you run out of gas, it will quickly come to a stop. So, keeping that in mind, you can see that a force is an object that can cause another object to change its magnitude or direction of its speed or velocity. Okay. Again, these were the word velocity wasn't really separate from the word speed in the day of Galileo, but Galileo very much had a sense of knowing that we needed to understand not only how fast something was moving and not only whether it was speeding up or slowing down, but also whether it was changing directions. So a force is anything that can cause an object to speed up, slow down, or change directions. Okay. A force is an object that can, or is a thing that can cause an object to speed up, slow down, or change directions. So that's what a force is. And your book does talk about like how it uses red arrows for forces and green arrows for velocity and stuff like that. So make sure you at least read through the chapter one time. But the main thing is when you're reading the chapters, you're trying to learn as much as you can. But if you don't spend as much time reading the individual paragraphs as a bare minimum, make sure you thoroughly read and understand the examples in all the chapters and subsections that we cover. So here's example one. It says, a school bus driver slams on the brakes and a bunch of book bags slide along the floor to the front of the bus. What force causes this? I want you guys to, when I ask these questions, especially conceptual ones like this, I want you to think of the answer yourself, try to come up with it. Even if you don't say it out loud, that's fine. I just want you to make sure you put your money down on a hypothesis of a guess and then learn after I give you the right answer. learn what made you go astray or learn why you got it right, and also jog your memory with the fact that you did get it right or you did get it wrong. So in this case, it says a school bus driver slams on the brakes and a bunch of book bags slide along the floor to the front of the bus. What force causes this? Well, given that we now know Galileo's law of inertia, we know that when the school bus is, let's say, going 35 miles per hour down the road, the school bus is going 35 miles per hour. All the kids in the bus, assuming they're not running forward or backwards or left or right, are also going 35 miles per hour. The book bags are going 35 miles per hour. The seats are going 35 miles per hour. The tires are going 35 miles per hour, so on and so forth. So when the bus driver actually slams on the brakes, what's going on is the individual book bags are attempting to maintain the status quo. They're trying to continue and obey the law of inertia, which says unless a force acts on the book bag, then the book bag's going to try to continue going 35 miles per hour. So what really happened that caused these book bags to come up to the front is that there was friction, probably some friction between the floor and the book bags, but those friction forces were insufficient to keep the bags from accelerating forward uh, to try to maintain their 35 mile per hour speed as the actual bus slowed down. Anybody have any questions on that? So it's not really it's not necessarily a force that caused the book bags to come to the front, but it was a lack of force that caused them to slide forward. So I'm just going to say due to Galileo's, actually, I think I was supposed to have two L's in there. It really should do better than that. Galileo's law of inertia, the book bags are trying to continue moving at 35 miles per hour, but the bus stopping causes friction forces to be required to keep the books from continuing at 35 mph. But the friction forces were too small. Now, example two. You'll see in section 4.1, they do talk about forces, but then they move to section 4.2 and they start talking about Newton's first law of motion, which, as I've argued, is the same thing as Galileo's law of inertia, except the wording's different. So again, I'm going to restate my version of Newton's first law of motion, and I highly recommend you either take the one from the book and memorize it, or you memorize my version. And I'll tell you that you can make it a lot shorter if you use the word velocity and the idea that velocity is a vector quantity. Okay, so without the use of the word vector, Newton's first law of motion says that an object in motion tends to stay in that state of motion unless acted upon by a net external force. An object in motion tends to stay in that state of motion unless acted upon by a net external force. Okay. Again, we can shorten that up by making use of vectors and specifically the velocity vector because there's some possible ambiguity when I say an object in motion tends to stay in that state of motion. We might say, well, what do you mean by that state of motion? What I mean by that state of motion is that the object will maintain a constant velocity. And remember, velocity is a vector quantity. So when you say something has a constant velocity, that means its speed and direction, its magnitude of the velocity as well as the direction of the velocity are going to remain constant. So another way of saying Newton's first law of motion is uh, an object tends to maintain a constant velocity unless acted upon by a net external force. I'm reminding you now that net, just like your net pay, is the sum of all the different forces acting on the object. And if that net gives you something other than a force of zero, then it is a net force. That's what we're using here is a net force other than zero. Okay. External force means it has to be a force applied to the system that you're studying by something other than another part of the system. So when you're actually studying things like imagining book bags, for instance, then you have to talk about the net external forces acting on the book bag. The net external part is basically adding up all the forces acting on the book bag. And the external part is since we chose the book bag and everything that's in the book bag is part of the system. So we can't count, for instance, the force that the books are applying to the insides of the bag or to the left side of the bag or the right side or the back side or the front side or the bottom side or any of that kind of stuff because those are part of the system and therefore they're internal forces. Okay. You can also imagine, for instance, the old thing of lift yourself up by your bootstraps. You know that that's physically impossible. So that's another way of thinking about external forces. You trying to lift yourself up by your bootstraps is you, part of the system, applying a force, lifting yourself up to you, part of the system, and therefore it can't be done. So that's another way of thinking about it. Anybody have any questions on that Newton's first law of motion? Okay. The way your book says it is every object continues in its state of rest or of uniform velocity in a straight line as long as no net force acts on it. So no net force is the same thing as saying a net force of zero, basically. So an object in motion tends to stay in that state of motion unless acted upon by a net external force. And he's not even bringing up the external part yet. That's why that's not in there. So let's look at in addition to Newton's first law, we have to have something, uh, partly because of Galileo's law of inertia being the equivalent of Newton's first law of motion. We need to have some sense of what an inertial reference frame is. So it turns out an inertial reference frame, the best way to describe it is a reference frame in which Newton's law of first law of motion or Galileo's law of inertia is valid. So that might seem a little contradictory, a little confusing, or something like that, but let's imagine this scenario. So I'm sure you've all been to a playground before and seen one of those big merry-go-round type spinning disc things, or you might have seen some on YouTube videos where people are making those playground things spin around really fast by putting motorcycle tires or mopeds against them and cranking the motorcycles or mopeds up and then having it actually cause the disc to rotate rather fastly. And then people get flying off like Sim City or something crazy like that. The main thing is think of that thing that you've seen in playgrounds before. It's big round disc. It's usually about 15, 20 feet across in diameter. It's horizontal. It's got these bars that run up, diagonally up, and then to a U like this. And people can run holding onto it to speed up and then jump on it. And then you spin around in a circle. It's like I said, I just call it a merry-go-round. But if you think of one of those for a second, and now you imagine building, some kind of structure on it so that you can hold a camera directly above the center of that merry-go-round. If you do that and you put that camera high enough where it can see the whole disc, but not so high where it can see off the disc at all, then you looking at that camera have no idea whether the thing is actually spinning or not, right? So if you took a basketball and stuck it dead center, it could spin ideally for a little while without that basketball moving if it really was at dead center. But to be honest with you, it's very, very unlikely that you could do it for very long because chances are the basketball is not going to be 100% balanced and its spinning is going to cause one part to lag off a little bit or something like that. But the main thing is if you're looking at that and you do not see that ball moving as if magic is occurring, because that's what it would look like if you're looking through a camera that's fixed to a merry-go-round, so that when the merry-go-round rotates, the actual camera rotates with it, and you see all of a sudden this ball that's just sitting there and it just speeds up and shoots out the side of the screen, that looks like magic. It looks like Newton's law of inertia was just violated. And that's why we call it, in that case, a non-inertial reference frame. However, if you did stick a basketball on there and it didn't move at all, that would more than likely be the case that it basically was not being spun or rotated. And if that's the case, then yes, the merry-go-round is an inertial reference frame. So example two, what is an inertial reference frame? And give an example and a counterexample. So an inertial reference frame is a frame that obeys Galileo's law of inertia. Now I'm keep using the phrase frame. Uh, I'll say coordinate system because that's sort of like what we're talking about. But a frame is sort of bigger. It includes the coordinate system and all the space around it, if you will. So an inertial reference frame is a frame in which Galileo's law of inertia is valid. So, and remember, Galileo's law of inertia basically says that an object in motion tends to stay in that state of motion as if it has some inertia, unless acted upon by a net external force. So, if you see anything not obeying Newton's first law of motion or Galileo's law of inertia, then it's clearly not an inertial reference frame. Uh, I asked for an example. So, a non spinning merry-go-round. Whoa. Can be, whoa, my pencil just became unscrewed or something. I just stopped writing. An inertial frame, a spinning, a spinning merry-go-round mostly cannot be an inertial frame. So you're probably sensing a little ambiguity in there, and that is correct. So what I mean by that is, for instance, our planet Earth is actually moving at a great velocity or in its orbit around the sun. It's also rotating about its axis at a very great velocity on the order of 1,000 miles per hour and on the order of 1,000 miles per hour, but even higher in orbit around the sun. And then, of course, the sun system, our whole solar system, is orbiting around the center of the Milky Way galaxy on a 250 million year period. All of those things are moving, yet in most cases, we can pretend like the Earth is sitting perfectly still and we don't get any violations. That's because, at least to the precision that we're doing the experiments, the Earth is an inertial frame. Even though we know, like I said, it is clearly accelerating, and since it's clearly accelerating, it clearly has the ability to have some magic non-inertial motion going on. Okay. Luckily, we don't see it too terribly often. Similarly, if we tried to study things very, very precisely, maybe to two, three, four decimal places, we might discover that all of a sudden our physics is starting to behave badly and not obey what we think is the laws of physics. And that's because the laws of physics that we're used to learning about and me teaching you about is for inertial reference frames. And if you go a little deeper, you can discover that the Earth is not a inertial reference frame. Has anybody ever heard of Foucault's pendulum or ever seen a pendulum that shows us the Earth is not an inertial reference frame? Anybody ever seen anything like that? So there's one at Smithsonian, I remember, and basically it swings back and forth, and if you watch it long enough, you'll see that it sort of sweeps out a complete circle. That is evidence that our Earth is rotating about an axis. So that's one of the ways you can actually see that the Earth is not yeah, exactly, in a museum. Yeah, thanks, Beth. But yeah, that's it. And that's Fouccalt, I believe. The spelling might be a little bit off, but it's roughly that spelling. There was a book called Foucault's Pendulum by, I can't remember his name anyways, but that was a good one. And Name of the Rose, Umberto Eco, that was the author's name. Umberto Eco, a really good writer, sort of like the guy that wrote, dang it, never mind. It was a Tom Hanks movie when they made it a movie, but I forgot the name of it anyways. But that's a good book if you want to check it out. And any of the books by Umberto Eco are really good if you're into that demonic Christianity, diatribe fight with good and evil and that sort of stuff. It's kind of neat. But anyways, that's enough about inertial frames. Anybody have any questions on that stuff yet? All right. Now, after we completed the section on inertial frames, mass, and forces, or excuse me, reference frames and forces and inertia and all that sort of stuff, I now am in the section that is called mass. So, what it turns out that what Galileo said would be inertia turned out to be basically our mass. And what I mean by that is there's a quantity that tells us how reluctant a particular object is to accelerate, and that object that's tending to limit an object's acceleration, that quantity or that physical quantity is what we call inertia and defined as inertia. Well, it turns out that if we double that, that's completely consistent with doubling the mass. If we cut that in half, that's completely consistent with cutting the mass in half. If we triple it, same thing. So ultimately, what we decided was an object's mass is a measure of its inertia or its reluctance to accelerate. Okay. It is also a property of the material or a property of the thing that you're looking at. So, for instance, if you ask Mr. Younger what's his mass, Mr. Younger will tell you my mass is about 116 kilograms. Okay. In some sense, you can say it's the amount of matter that makes up Mr. Younger, and that's right. But I've never found that definition very good for mass. Uh, you can sort of think of it as, well, I know individual neutrons, protons, and electrons have a quantity of inertia, and we know that they obey Newton's laws of motion and that they have specific masses. And if you added up the specific masses of our atoms and put them all together, you would get a total mass, and then that would actually be the result that is called my mass. So, for instance, if you added up the mass of all the atoms and molecules in my body, uh, such that you never, duplicated counts and never left off any atoms or molecules, then that number would ultimately be my mass, which is a measure of my inertia. So that's another way of thinking about it. There's another side of this that's quite different, and that's our weight. So when we talk about an object's weight, what we mean is some other body's affinity for that object. So when you talk about the weight of Mr. Younger, it really is asking what affinity the Earth has for Mr. Younger. So Mr. Younger, the Earth has a affinity for Mr. Younger that equates to about 255 pounds. Now, in terms of newtons, that is 1,136.8 newtons. So you can see a newton is quite small. And a newton turns out, by the way, to be the unit that we use for force in the SI system. And once we have Newton's second law of motion, you'll see exactly where the newton comes from. But right now, just know that the newton is about a quarter pound. So it weighs a little less than a quarter pound. Uh, so in some sense, if you have a number of newtons, if you divide that by four, you'll roughly get the number of pounds. It's not exactly four. Your book has the conversion factors. But the main thing is you need to know there's a difference. There's a quantity that is a property of the object. So for instance, if the object that you're talking about is your teacher, then your teacher has a specific quantity that's very important, and it's about him personally. That quantity, though it does change, obviously, by small amounts, even during the hours, like within 1 hour, you can change your weight significantly, and your mass significantly. So, but that's what I'm talking about is there's a property associated with me that is my reluctance to accelerate. That property happens to be my mass, and my mass is about 115 kilograms. Okay, 116 is what I called it. Now, that is a property of me. Again, it's a property of me that changes. So, like if I eat a bunch of food, it's going to go up immediately. If I, go and run a mile and then, get cleaned up, dry off all the sweat off of me, then I'll probably weigh a little less as well. But it's still my property, and it's always going to be about me. No matter where I go, it will always measure my inertia. Then there's this other quantity, which can sort of be thought of as a property of me, but it's also a property of the planet that I'm on. And that's the desire that the planet has for me, or how badly the planet is pulling on me. That quantity is called your weight, and that is measured as a unit of force. And the unit of force that we use in the SI is the Newton, whereas the unit of mass that we use in the SI is the kilogram. Okay. So, with that in mind, we're looking at example 3. It says, on Earth, your instructor's mass is about 116 kilograms, and his weight is about 1,137 newtons. What would be his mass and weight on the moon? How about in outer space, many light years from any other masses? So, on the moon, Mr. Younger's mass, which is a property of Mr. Younger, will still be 116 kilograms. However, his weight would be how strongly the moon pulls on Mr. Younger. That quantity is weight on the moon is equal to 116 kilograms times acceleration. The acceleration on the moon is 1.633 roughly, and that's meters per second every second, or meters per second squared. And when I multiply those two quantities, I get 189.5 newtons. So that would be my weight. And I'm going to give you the formula for weight in a little bit, but like I said, I'm just using it right now. So on the Earth, my mass was 116 kilograms. On the Earth, my weight was 1,137 newtons. Whereas on the moon, my mass is 116 kilograms as well, but my weight, which is how much the earth or the moon is attracted to me, is more like 189.5 newtons. So you can see that the weight actually changes from to location. So different locations obviously cause different weights. And that leads me to the second part. It says, how about in outer space many light years from any other masses? Well, when you talk about an object's weight, you should always be realizing that weight is a gravitational thing. So you have to have a gravitational pull in some sense. You can mimic a gravitational pull by, for instance, making a space station that spins. If that space station spins and it's round and you're like on the inside edge of the tire, uh, your natural tendency is to be pushed downward in some sense towards the outer edges of that tire, and therefore it looks a lot like weight. It's not technically a gravitational force, though, so we're making an artificial weight force by causing the space station or spaceship to rotate. But in terms of weight, you normally need a gravitational force to do that. And in order for you to have a weight, you have to have a big gravitational body to be on for you to have that weight. So when you're in outer space, not necessarily like in orbit around the Earth or in orbit around the moon, because clearly you're way close to the Earth and the moon then, and the gravity of the Earth and the moon are definitely pulling on you at that point. But what I'm saying here is imagine that you got many, many light years away from any mass. So there's no planets, there's no stars, there's no ginormous gas clouds, there's no black holes, no neutron stars, no red dwarfs, no brown dwarfs, none of that kind of stuff. Anywhere within a measurable distance from us. In that case, you have no weight. Weight does not make any sense whatsoever. But guess what? Your mass is still 116 kilograms. So, uh, in outer space, far from any other masses, your weight is meaningless, I'll say, but your mass, or I should say my mass, and I'm sorry, I switched to your instead of my. Now I'm switching that back. My mass remains 116 kilograms. Now, I want to, while I have you here, I want to go ahead and express something to you. So, the units we use in America, us and Myanmar, I think, we use the British system. Ooh. And in the British system, we have a very specific set of units. So, for instance, for mass and for force, which by the way is the same thing as I sort of say it's the same thing as weight. Weight is measured as a unit of force, but not all forces are weights. Okay, so that's why I'm saying that. So within the British system, the mass is technically the slug, and the force is the pound, which we often abbreviate this way, but we also abbreviate LB. And then in the SI, the unit of mass is the kilograms, and the unit of force is the Newton. There's also a CGS, which is like the SI system, but it's the SI system before we made it more rational. And when we made it more rational, we started dealing with units of mass in kilograms instead of grams. And we started using units of meters instead of centimeters. So that's pretty much the only difference is within the CGS system, the unit of length, the fundamental unit of length is a centimeter, and the fundamental unit of mass is the gram. So in this case, the unit of mass for the CGS would be grams, and the unit of force would be dynes, which is you've probably heard the phrase dynamometer before. That's why we use dynamometer is because a dyne is a unit of force. Okay. All right. Well, that's a pretty good breaking point. We've been going for an hour and 15 minutes. So let's go ahead and let's take a 7 minute break this time. So let's be back at 6:52. And I'll be here the whole time, and I'll be making announcements at about 2 minutes till, and then 1 minute till, and then we'll start up. But you can go ahead and take a break, and you can feel free to ask me questions while you wait.
I had a question about the lab due tonight, lab three. Uh,
Okay.
is there a doc posted
Ah,
for
yes,
that?
lab three, we had some problems. Now, Kaylee, you're in my 001B, right? Not my NO2B.
Yeah, that's correct.
Okay, just want to make sure. So yeah, I sent out an email about that yesterday to actually no, you know what? I don't think I ever got around to sending that email. I posted, it might have been the day before, but basically we have a problem with this, the lab. I'm still trying to locate a link from the makers of our software so that you guys can download the software. I haven't been able to get a hold of anyone yet. So that lab that would have been due tonight, lab three, you have at least 7 more days to do it, was what I told everybody, and you might even have more than that. Once I finally get the link or find some way to fix it, I'm going to give you a whole nother 7 days.
Okay. Thank
Okay.
you. So it's not due tonight then.
Yeah, yeah, definitely not due tonight.
Okay, thank you so much.
You're welcome. Thanks for asking me, Kaylee. It's good for me to run. Do you remember getting an email from me about that? I want to say maybe it wasn't yesterday. It was maybe Tuesday night, maybe that I think I sent it out.
I can double check.
Yeah, I thought I sent that. That's bad if I didn't, but I was pretty sure I did. It's crazy. That was not what I was looking for. My wife keeps sending me these cute little AI things of babies like being Donald Trump or babies being figures on Big Bang Theory and stuff. They're just so cute. They crack me up. I don't know why I'm talking about that, but just for fun. I'm looking in the emails. Don't see it there. Let's see. No, there.
I found the email.
You did found it? Okay.
Yeah.
Good. I was afraid I had forgotten to. I did have one email that I ended up not getting to send out until today, and that was just about the me moving the date. So I was afraid I might have done the same thing with this one, but I guess not. Cool. Thanks, Kaylee. I'm glad you were able to find that, and even faster than me.
Thank you.
Still got about 4 more minutes. Got about 2 minutes left. Got about 1 minute left before we start back over. Hey, baby. I'm in class right now. Is everything okay? Okay. I won't get out till about 8, so I'll give you a call when I get done. All right? All right, love you too, baby. Bye-bye. All right, it's about time to go ahead and get started. Just to give you a little peek of what's to come and to make some sense, this what I'm getting ready to tell you is something that will come in handy throughout the whole semester. So I wanted to go ahead and show you right now. So for starters, what we're getting ready to introduce is Newton's second law of motion. And Newton's second law of motion you can sort of look at as Newton's first law of motion in a special case. So remember, Newton's first law of motion is an object in motion tends to stay in that state of motion unless acted upon by a net external force, or an object tends to maintain a constant velocity unless acted upon by a net external force. What happens if the net external force is not zero? If the net external force is not zero, then you actually have an acceleration, and that's when Newton's second law kicks in. And Newton's second law basically says that the acceleration is A, and that acceleration is directly proportional to the net force. So instead of just writing an F, I write an F with a sigma on it. And that sigma means, like you know from algebra and calculus, that means a summation. So it has to be the sum of all the forces acting on the body. So the acceleration is directly proportional to the total force, but it's inversely proportional to the mass of the body. And it's technically in the direction parallel to the net force. So I can put vectors on it. Once we have that, we can see that F is equal to M times A. So we can figure out exactly what the unit of the force is. The unit of force, which is the summation of forces, is equal to the unit of mass times the unit of acceleration. Now I'm going into unit analysis, not to be confused with dimensional analysis. The only difference being in unit analysis, we use M for meters for length, and we use capital L in dimensional analysis. We use capital T in dimensional analysis for time, but we use lowercase s for seconds for time in unit analysis, and so on and so forth. So I can look right here and see that the unit for mass is the kilogram, and the unit for acceleration is meter per second, and therefore it's kilograms meters per second squared is equal to 1 Newton. So that's what an actual Newton is. Additionally, you could work this out for the CGS system, in which case you would get grams for the unit of mass, and you'd get centimeters per second for the unit of acceleration. And this gives you grams, centimeters per second squared, which is defined to be 1 dyne. And you can see that the dyne is going to be a really small number, because to get from a dyne to a Newton, you'd have to multiply by 1,000 to get from grams to kilograms, and then you'd have to multiply by 100 to get from centimeters to meters. In other words, you need 100 centimeters to make 1 meter, and you need 1,000 grams to make 1 kilogram. So you expect the dyne to be like 1/100,000th of a Newton, and that would be about right. So hopefully that helps you better understand why these units are what they are. But keep that in mind. These fundamental unit breakdowns of the Newton and the dyne are extremely important. You'll be using them probably for the rest of your life. If you really do become an engineer or a physicist or maybe even a chemist, then chances are you're going to be using this for the rest of your life. But that's about it as far as the separation between mass and weight. I will calculate using Newton's second law in a second. I will calculate the formula for weight, and that'll make more sense to you then. All right, this brings us to Newton's second law, which I sort of just explained to you a little bit. I said that Newton says basically an object, if it has a net external force acting on it, then that object will no longer be subject to the uniform motion that Newton's first law or Galileo's law of inertia says we'll get. It's actually going to have a motion that can change direction or change speed. And in order for that to happen, it has to be the acceleration is directly proportional to the net force and inversely proportional to the mass. So that if I double the net force, that doubles the acceleration. Thumbs up, thumbs up. If I double the mass, though, that cuts the acceleration down by a half because it's that's a thumbs up, thumbs down representation. Remember, when I say thumbs up versus thumbs up, thumbs down, what I mean by that is I'll write it right here in green just to make some sense of it. Let me get green out here. So y equals k times x is thumbs up, thumbs up. That's the thumbs up, thumbs up. And you can see that the two variables, y and x, are on opposite sides of the equals, but they're on the same side of the fraction. So, in other words, there's no fraction on the left, so that means you can write y over 1. There's no fraction on the right, so that means you can write x over 1. And when you do that, you see both y and x are in the numerator. So when they're in the same part of the fraction, but on opposite sides of the equal, that's thumbs up, thumbs up. Similarly, if you had y equals k over x, then you have oops, thumbs up, thumbs down. So that's what I'm calling like this. And it can be a little bit more advanced than this. It could be y equals k over x squared, just like it could be y equals k times x squared or y equals k times x cubed. Those would be thumbs up as well. And the y equals k over x squared would be thumbs up, thumbs down as well. Just they wouldn't be represented by if I double x, then I double y. If the x was actually squared, doubling x would quadruple y, tripling x would nine-tuple y, so on and so forth. Similarly, in the thumbs up, thumbs down, if I doubled x, then y goes down by a factor of 2. But if it's y equals k over x squared, then doubling x would make y go down by a factor of 2 squared, which is 4. So that's the key to understanding this A equals F over M. So A and the summation of the forces are both in the numerator, but on opposite sides of the equal. So A and the net force are thumbs up, thumbs up. But A and the mass are on opposite sides of the equal symbol, but they're also on opposite sides of the fraction bar. So that means they're thumbs up, thumbs down. Does anybody have any questions on that? Does that make sense to everyone? I'm sorry I sort of put it in there in a higgledy-piggledy way just to make sure I fit it in green, but hopefully that was enough to explain to you guys. No questions? All right, now would be a good time for you to go ahead and send me a chat with your first and last name. If you are here from the O01B class, please write O01B or asynchronous with your name. So I have that in there. Now that I have this idea of what Newton's second law is, that specifically, it's normally written the summation of forces is equal to mass times acceleration. So that's the way we're going to tend to write it from here on out. But I just want to make sure you remember I use the summation, the sigma symbol, to remind you to add them all up. And I also use it in vector symbols so that we end up having one equation for each dimension. So I'll show you that in this problem. So example 5, estimate the force needed to accelerate a 1,000 kilogram car at 1/2 g, and then two, a 200 gram apple at the same rate. So solution, what we know is Newton's second law, summation of forces is equal to mass times acceleration, but this means the summation forces in the x direction equals mass times acceleration in the x direction. Summation forces in the y direction equals mass times acceleration in the y direction. And the summation of forces in the z direction equals mass times acceleration in the z direction. That's what this vector equation partly does. By writing a vector equation, you're covering all three dimensions in one equation. But when you go to apply it, oftentimes you have to break the individual forces and accelerations down into individual components and put them in individual equations, work out what missing variable is, and then plug that back in to make a new total acceleration or a new mass or a new total force. So that's what I'm using here. And for part one, as we call it, namely, I did one instead of A because I couldn't fit an A between the A and the, and the acceleration. So I just stuck a number one in parentheses. So what I have is m is equal to 1,000. Notice I knew it's m because its unit was a kilogram. Now the acceleration is a little different. The acceleration is 1/2 g, and this is where the terminology g forces comes from. So when you have a force big enough to cause you or something an acceleration of 1 g, then that means your acceleration is 9.8 meters per second every second. If it's 2 g's, it's 2 times 9.8 or 19.6 meters per second per second. And of course, if it's half a g, it's 4.90 meters per second every second. So in this case, I've got that, and what we want to know is summation forces equals question mark. Now they're asking us to estimate the force. So what I'm doing here is I'm saying the summation of the forces is equal to a question mark. Another way of looking at it is I'm imagining there's only one force acting on it, and I'm figuring out what that force would have to be to cause this acceleration. That's another way of looking at it. But the key thing to remember here is just because you double a particular force on a particular mass, that doesn't mean you're going to double its acceleration. It's only going to double its acceleration if the total force acting on it is doubled, not a particular force. Everybody understand the difference between me saying a particular force and the total force? Make sure you ask me if you don't understand. It does look like a lot of you chatted me your first and last names. Please continue doing that if you hadn't done it already. I'm going to continue now. The net force, in this case, is just one dimension. I'm just imagining a car going along the x-axis, for instance, and then I'll say the summation forces in the x direction is equal to mass times acceleration in the x direction. The mass is going to be 1,000 kilograms, and the acceleration is going to be 1/2 of 9.80 meters per second every second. Now, this is the part where they say estimate. So in reality, when they say estimate, I'm going to assume this is approximately 10. Therefore, I'm basically multiplying 1/2 times 10 to get 5, and then times 1,000. So this would be around 5,000 newtons. So that's the approximate force necessary to accelerate a car at an acceleration of half of the acceleration due to gravity. Now remember, 5,000 is about 5,000 newtons. A newton is about 4 newtons is about 1 pound. So if I divided 5,000 by 4, I would get by 2 would be 2,500, by 1 would be 1,250. So yeah, 1,250. So this is about 1,300 pounds of force. Okay. On the order of almost 3/4 of a ton. Now let's do part B, or part two now. So for part two, the mass is equal to 0.200 kilograms. This is the key point. I told you guys we're using the SI. That means all the equations we get in this book, unless it explicitly tells you otherwise, has to be put in for mass in units of kilograms, for acceleration in units of meters per second, and units of force, newtons, so on and so forth. So I've got to convert that 200 grams to kilograms, which is what I did there on the fly. Hopefully y'all recognize it. And A is equal to 1/2 G, which I'm going to say is approximately 5 meters per second per second. So in this case, the summation forces in the x direction equals mass times acceleration in the x direction is going to give us 0.200 kilograms times 5.00 meters per second. Now, by or zero point 0.2 happens to be 1/5. So in this case, the answer is approximately 1 Newton. Okay. So a 200-gram apple takes about 1 Newton of force, which is about a quarter pound, whereas a 1,000 kilogram car takes about 1,250 Newtons. Anybody have any questions on that? So we're starting another problem here. It says, what average net force is required to bring a 1,800 kilogram to rest from 100 kilometers per hour within a distance of 60 meters? And then in the other part, I ask, what about within a time, and I put the time in all caps so you'd recognize the difference, of 3.40 seconds. So I'm going to say solution. Here's where I write down the information I know as well as the equations I'm using. And sometimes I say some things or write down some things to help me uh, figure out the answer. So right now what I'm going to say is the summation of the forces is equal to mass times acceleration. I'm also going to say that the mass is equal to 1,800 kilograms. I'm going to say V final is 0. I'm going to say V initial. Now, here they've given it to us in 100 as 100 kilometers per hour, but we have to actually convert that to meters per second uh, for us to be able to use it in any of our equations, really. So I'm going to go ahead and convert this. What I know is 1 kilometer is equal to 1,000 meters. And what I also know is that 3,600, or excuse me, 1 hour is equal to 3,600 seconds. So what I end up doing is dividing by 3.6. So dividing 1,000 by 3.6, or excuse me, 100 by 3.6 gives me the velocity in meters per second. So that's going to be 27. Oops. That just went really badly. That's 27.78 meters per second. Notice how I carried an extra sig fig. I'm also pretending like the 1,800 has 4 sig figs. So just be mindful of that. For part A, I have the delta t, excuse me, I have X is equal to 60.0 meters. And in order for us to do this, we want to find the total force because it's asking what the net average force is, but we can't do that until we find the acceleration. So I've got to find the acceleration. I have a final velocity, I have initial velocity, and I have a distance. Hopefully, you guys are like going crazy trying to tell me exactly what kinematic equation to use. Hopefully, you've all thought of it. I'm getting ready to write it down now. The equation I'm going to use is v squared is equal to v0 squared plus 2ax minus x0. That's going to allow me to calculate the acceleration. So I'm going to say v squared, which is the final velocity, that'd be 0 squared, is equal to 27.78 meters per second squared plus 2 times a, which is what we're actually asked for. So I'm just going to write that as an a instead of parenthesis. And then x minus x0, I'm going to assume x0 is 0. You can always make the x0 0. It's okay to do it at any time. I'm doing it. X I'm going to call 60.0 meters. And from that, you can see that a is going to be 27.78 squared. Ooh. And then I'm going to divide that by 2 times 60. So I'll say the square of 2778 turned out to be 771.7284. I'm going to divide that by parentheses 2 times 60, close parentheses. That's going to give me an acceleration of negative 6.43107 meters per second every second. Now, really what I had was 3 sig figs divided by 3 sig figs. So the 1, the 0, and the 7 are not sig figs. I'll keep track of them anyways. And I'm also going to throw the negative away. The negative is just showing us in this case, in these coordinates that I've sort of imagined, even though I didn't think about them for 1 second, in this coordinate system, I have slowed down and in such a way that it caused a negative acceleration. All I care about is the magnitude. So now I'm going to take the summation of the forces is equal to mass times acceleration. And the mass is going to be 1,800 kilograms. And the acceleration is going to be 6.43107 meters per second per second. And that gives us 11,576 newtons. And of course, we again use 3 sig figs, so the 7 and the 6 are not significant figures, but that gives us an answer for the first part. Now for the second part, this time I'm going to use A is equal to V final minus V initial over T, which of course V final is going to be 0. V initial is 27.78 meters. Oops, that's not acceleration. Oh yeah, that is meters per second. Sorry. I think I said acceleration, but I meant final velocity, or initial velocity in this case. And now I'm going to divide this by 3.40. So 27.78 divided by 3.40, that gives me 8.171 meters per second every second. That's one extra sig fig. I could have put more. It was 170,588, so on and so forth, but carrying one extra is sufficient. So now I'm going to say the summation forces equals mass times acceleration is going to be 1,800 kilograms times 8.171 meters per second per second. And this gives me 14,707 newtons. And again, this is only 3 sig figs, so the 0 and the 7 are not sig figs. So stopping it in a distance of 60 meters only required a force of about 11,600 newtons, but stopping it in 3.40 seconds required a force of about 14 8,700 newtons. Any questions on that? All right, so that's Newton's second law, and hopefully that makes some sense to you. I want to repeat it again just so you'll have the wording and the sense of what it means. Basically, the way Newton said it, and remember, they didn't have a lot of easy ways to make equations and stuff like that, so a lot of stuff had to be done just with words. So, uh, when an object of mass m is subjected to a net force, then it experiences an acceleration A that is directly proportional to the net force and inversely proportional to its mass, but it also happens to accelerate in the direction parallel to the net force. So once you add all the net forces, or all the forces together to get the net force, you get a force, which is a vector quantity that has a magnitude and direction. We're saying the acceleration is proportional to that magnitude, but the acceleration is also parallel to that force direction. Okay, and it's inversely proportional to the mass. So that's the real crux of Newton's second law. That's what you need to understand to figure out how to accelerate things. And that's why this particular chapter is called dynamics. Remember, kinematics is the study of motion without respect to what's causing it to have that velocity or that acceleration or whatever. Uh, Dynamics is when you try to say, well, how do I make something accelerate, or how do I make something get up to a certain speed? So that's Newton's second law. Hopefully that helps all of you folks. I'm trying to look and see if there's anything else I want to jump in. It seems not. Your book does discuss a very precise definition of mass. I'll leave that up to you to read, but you can ignore it. I will tell you the last section, or the last of Newton's three laws of motion, is Newton's third law. So my dogs are going crazy because my wife just got home. So I apologize for oh, my cat's going crazy too. So I apologize for the noise in the background. Newton's third law of motion. So you've learned Newton's first law of motion, and you've learned Newton's second law of motion. Now you're learning Newton's third law of motion. I'll give you the generic warning that I give all my students. If you have a chapter or a subsection in a textbook and it has a name that's like the name for a particular equation, or the name actually includes the word law, then there's a high probability that that particular equation or that particular law is extremely important. And no matter what class you're in, I highly recommend that you memorize verbatim exactly what each of those laws would be. So in this case, we've got Newton's three laws of motion: Newton's first law of motion, Newton's second law of motion, Newton's third law of motion. I highly recommend that you commit them to memory, because occasionally teachers try to be nice and give you what they think is a really easy question. And that easy question might be, which one of the sentences below is Newton's first law of motion? Which one of the sentences below is Newton's third law of motion? Which one of the sentences below is Newton's second law of motion? So on and so forth. Uh, if you have it memorized verbatim, then you can recognize it verbatim, but you can also, figure out when they try to paraphrase it or something like that. But the main thing is always commit those to memory, or you can suffer the same consequences as me, where sometimes I just didn't take the time to do such things, and I lost, easy points on tests. So hopefully I will learn from my mistakes. But in Newton's third law of motion, I'm going to give you a couple different ways of stating it. Let's say one version: you cannot touch without being touched. This is one that I saw in a book. I think the title was something like Physics for Art Majors or something like that. So you can see it's a little, a little touchy-feely, a little tree huggery or something like that. You cannot touch without being touched. And it's really not a good version, but it's a nice version in that it tells you part of it, but it's a bad version in that it doesn't tell you the main part. Uh, Another version is uh, for every action. Can anybody finish this for me? For every action,
There's a reaction.
pretty close. Yep. There is an equal. This is the part you left off, but that is another version I've seen it in one of those conceptual books. Is they just say for every action there's a reaction. That actually is one of the versions, but it's not specific enough. So I'm going a little deeper. For every action there is an equal but opposite. And if my pen stops turning into an eraser, that'd be great. And I don't know why I capitalized that reaction there. So for every action, there's an equal but opposite reaction. That's getting a little closer because that tells you that yes, there's a force, but there's a reaction to that force, and the force reaction is equal, meaning the same size, but opposite, meaning the opposite direction. Again, it lacks some of the terminology, like it doesn't say what it means by equal but opposite. So it's not really that complete. In fact, the best way is the equation form, in my opinion. And I'll do it like this: the force on object A as a result of object B, and notice it's a vector quantity, so that means it has magnitude and direction. And when you have an equality between two vectors, that means their magnitudes are equal and their directions are equal. So the force on object A as a result of object B is equal to the negative of the force on object B as a result of object A. That is way more precise because it tells you explicitly what we mean. So if, for instance, I kick a soccer ball, there's a force that my foot applies to the soccer ball. So I would say the force on the soccer ball due to my foot is equal to the negative of the force on my foot due to the soccer ball. So if I were to wear special shoes that would automatically tell me what force my kick applied, and I go up and kick a soccer ball, and the little special shoe tells me, oh, you just kicked that with a force of 300 newtons, then what I would know is that the actual uh, soccer ball experienced a force of 300 newtons, and it was in the direction that I kicked it. What this equation now says is that my foot felt a force of 300 newtons, only it was in the opposite direction as the way that the ball went. So that's what the negative is there. Remember, when you multiply a vector by a scalar, if the scalar is positive, you don't change the direction at all. But if the scalar is greater than one, you increase its length. And if it's less than one, you decrease its length. And if the scalar is negative, you reverse the length. So in this case, we're just multiplying by -1. So in this case, we mean that the force is equal in magnitude but opposite in direction. So hopefully that makes sense. Equal in magnitude, but oops, I wrote bot there, but opposite in direction. So hopefully that's enough to help you explain, understand a little bit about Newton's third law. There's a bunch of different ways of looking at it. One of the ways that I learned in my teaching conceptual physics classes that I think is kind of nice is if you've ever like tossed a tissue or a single square of toilet paper up into the air and tried to hit it real hard, I know that's not something that people do on a regular basis or anything, but give it a try now because it's something that you can do really easy. So I'm literally talking like a Kleenex or something really, really light, like a Kleenex or a single square of toilet paper. Just put it up in the air and like try to hit it really, really hard and see how unsatisfying it is. Okay. Additionally, and a little more cruelly, but probably you've experienced this. If you've ever tried to hit like a mosquito or a fly while it's in the air, you'll notice something weird. It's like all of a sudden they're like little The Rock or some other kind of tough guy or something like this, and in that you hit a fly and he's like falls over and then he just flies off a little bit and he's sort of stuttering, but he's just fine. And you literally like swung with all your might to try to kill that sucker, and he's just fine. Well, there's a good explanation for why that's so, and there's an easy explanation for why that's so. And if you can make the correlation between the good and the easy explanation, then you'll have a better understanding of motion in general as well as Newton's third law of motion. So, one way of thinking about why it's so hard to hit really hard a tissue paper or a square of toilet paper or a fly is that you cannot apply any bigger force to the fly or the tissue paper or the toilet paper square than the fly or the tissue paper or the toilet paper square can apply to you, right? Newton's third law says whatever force you apply to the fly, the tissue paper, or the square has to be equal in magnitude to the force that the fly, the tissue paper, or the square applies to you. That is somewhat satisfying, but doesn't necessarily explain to me why or anything. So I'm going to go a little deeper. The little deeper is this. Let's solidify it by just talking about the fly so it's a little simpler to deal with. So what we're going to imagine here is we have a fly in the air. So there's our little fly in the air. Its velocity is about 0. Okay, so this is our little fly. He's awful cute. He stole a piece of my cheese. Okay, now remember, this fly is very, 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 very small. That means its mass is very, 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 very small. So it's not unreasonable, for instance, to think that the mass of a fly might, in fact, be just a couple grams. Okay, if that's the case, then remember you're going to have to divide that mass by 1,000 to get it into kilograms. So it's going to be even smaller. And remember that the acceleration an object gets is directly proportional to the net force acting on the object, and it's inversely proportional to the mass of the object. So if you think about me trying to hit the fly, imagine me a professional baseball pitcher, which I'm not, but let's just pretend for a second that I am. If I'm a professional baseball pitcher, I know that some professional baseball pitchers, or at least that guy that was at University of Tennessee 3 years ago, who was pitching like 107, 110. I know that I should be able to throw about 100 miles per hour. Okay. So if I can throw a ball at 100 miles per hour, imagine me getting my arms swinging as fast as that when I go to hit this fly. That would mean my hand is moving at like 100 miles per hour. Okay. Now, what's going to happen is I'm going to hit that fly, and in order for me to hit that fly, I've got to make contact with him, and then he's going to compress a little bit and then speed up to sort of ride along my hand, meaning he's probably not able to fly 100 miles per hour. So even if he bounces off, he's not going to be able to fly and stay ahead of my hand, especially if I hit him dead center. So when I hit him at 100 miles per hour, he's going to have a small amount of time where his body gets hit and he compresses just a little bit, say on the sides of his body as my hand is hitting him. But in a very short period of time, he's going to accelerate from 0 miles per hour up to 100 miles per hour. And that force that caused that acceleration is the force I'm applying to him. So if you think about it that way, then you can see that the force, the net force, is equal to mass times acceleration. If you now say, wait a second, that force has to be enough to bring the fly up to 100 miles per hour, then I have to figure out what that acceleration is. That acceleration could be pretty big. It's going to be like 100 miles per hour minus 0 miles per hour, and it's probably going to be on the order of a tenth or even a hundredth of a second. So we can say 100 miles per hour. And of course, we can also convert 100 miles per hour to meters per second. And I actually have another calculator that does that instantly. It's kind of nice. So I'll do that really quickly just to make it easy. So 100 units of speed, miles per hour. I'm going to add to that 0 meters per second. And that automatically converts to 44.7 meters per second. So the acceleration would be 44.7 meters per second minus 0 meters per second. And then I'm going to divide that by, let's assume it's a bigger amount of time, meaning he's going to be in contact with me and accelerating over a whole tenth of a second instead of a hundredth of a second. We're going to say 0.10 seconds. We can see that this gives me 447 meters per second. And if I quickly Google mass of a housefly, mass of a housefly is 5 milligrams to 15 milligrams. Let's take that fat one. M is equal to 15 milligrams, which is 0.015 grams, which equals 0.000015 kilograms. So now the net force required to accelerate this fly is 0.000015 kilograms times 447 meters per second. And in this case, you get 447 times 0.000, whoa, 447 times 0.000015. And this gives me 0.0067 newtons. So physically, that is actually why you can't hit a fly or a piece of tissue paper or a square of toilet paper very hard. Specifically, the mass is so low that it accelerates with almost no force. And yes, the fly might get a little stunned, might get a little headache, or might be a little confused for a little bit. But generally, they're not going to experience much force. Okay. And that's all because, like I said, it turns out Newton's third law limits the amount of force that an object can apply to you, as well as the amount of force that you can apply to an object. So that's the reason we can't really hit a fly very hard or hit tissue paper in the air very hard or anything like that. A good question, and this brings in the Newton's third law of motion. A good question is exactly what makes a car move. So, what is actually applying the force? Where is the force applied to the car, and what is applying the force to the car when a car accelerates? I want you to think about that a little bit and try to guess before I explain it to you. So, what I'm going to tell you from inside the car, what happens is the car's running, it's sitting still on a road or on a racetrack or whatever, and it's running. And let's assume it's automatic, so I don't have to detail the shifting of gears and stuff like that. But I hit the accelerator really hard. The accelerator being hit really hard basically makes a bunch of fuel cascade through the fuel injectors or the carburetor into ultimately, after being atomized, into the piston chambers of the engine, which might be a V8 or a V6 or a V4, or it might be a Tesla, in which case it has no cylinders, it's an electric motor, and it wouldn't have any gas going into it. It would have some current going into a motor. But the main thing is, either way, you're going to get some kind of power or energy coming out of the motor system. That motor slash engine system is going to turn your transmission, which will turn your drive shaft, which will turn your differential, and therefore your two axles on each one on each side, and cause the wheels to attempt to rotate. Now, when the wheels attempt to rotate forward, the only thing that's going to keep them from freely rotating forward is the friction between the bottom of the tire and the road. So as you hit that accelerator really hard, its intent is to spin the wheel really fast in the forward direction. If that friction is sufficient, then instead of it spinning really fast, it'll spin as fast as it can, but it'll only spin as fast as it can without the tire slipping free of the road. So ultimately, what happens is it spins like this to go for the car to go this way. It spins like this direction, and applies a force to the ground this direction. Newton's third law says for every action, there's equal but opposite reaction. So whatever force that tire is putting on the road surface due to friction, the road surface is putting the exact same force forward on the tire, and it's forward because it's equal but opposite. And that's actually causing the car to move forward. Okay. So it literally is the friction between the tire and the road causing the tire to not be able to spin freely, but to rather grip the road, and the road then pushes the car along. That's the value of Newton's third law. Not only does Newton's third law tell us stuff about why it's hard to kill a fly in the air, it also, a lot of times, is the only reason that we can use Newton's second law. Like if I was a robot and I had all these wonderful mechanisms built inside of me, or apps built inside of me, such that when I took off, it would tell me exactly what forces I applied to everything. If I punched somebody, a heads up display would come up and say, wow, you really did well. You hit that person with 7,000 newtons of force, or blah, blah, blah. Right? If I had all that cool technology, and I just tried to figure out, well, I wonder how high my acceleration is when I take off from starting blocks and try to run. What I would do is I'd get in those starting blocks and take off running, and then my heads up display would say, congratulations, you just pushed backwards on the starting block with a force of 7,000 newtons, blah, 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 or something like that. Well, guess what? I still can't use Newton's second law to calculate my acceleration. I know my heads up display tells me my mass. I know my heads up display tells me the force that I applied to the starting blocks. But Newton's second law says the forces acting on an object of mass m creates an acceleration a given by the net force summation of F divided by the mass m. I can't do anything with that though, because I don't know the force that the blocks applied to me. I only know the force that I applied to the blocks. Well, good news. Newton's third law says if you applied a force of 7,000 newtons backwards to the starting blocks, then the starting blocks applied a force of 7,000 newtons forward to you. Therefore, I know that particular force is 7,000 newtons. I could work out any other forces like friction, resistance, all that good stuff. I could put those in there, but the main thing is probably the biggest one would be that 7,000, and it's so much bigger than all the other ones. You might even be able to ignore it as a round off error, put that in the F part for F equals ma, put my mass in the M part, and now I can solve for the acceleration. Anybody have any questions on that? All right. Your book has a conceptual example. It says Michelangelo's assistant. Let's show you this real quick. Stop share. Now I'm going to share my screen with you. So here's the example I'm talking about, conceptual example 4.5. Michelangelo's assistant has been assigned the task of moving a block of marble using a sled, see figure 412. He says to his boss, when I exert a forward force on the sled exerts an equal but opposite force backward. So how can I ever start it moving? No matter how hard I pull, the backward reaction force always equals my forward force, so the net force must be zero. I'd never be able to move this load. Is he correct? Anybody have any thought? I want you all to think about what the answer to this is, and I want you all to have your own answer. And I'm sort of stalling right now so that y'all can think about it. But I want you all to think about this answer before I give it to you. Would anyone like to tell me what's wrong or what's right about this or try to answer it? If not, I can do it myself, but you're welcome to if you think you know it. You're also welcome to if you don't think you know it, but you want to give it a guess. So the key here, it looks like no one's stepping up to actually answer it, and that's fine. I prefer y'all to be a little more interactive, but that's okay. Sometimes you just don't know stuff, and that's okay too. So what I'm going to say is the wording here is extremely important. It says, when I exert a forward force on the sled exerts an equal but opposite force backward. Notice it said the sled applies an equal but opposite force. It told us the force that the sled's applying. It tells us that its magnitude is equal, that its direction is opposite, but it didn't tell us what it was actually acting on. So, what is the force that the sled is applying? What is that acting on? Anyone? All right, let's try the first part over again. It says, when I exert a forward force on the sled exerts an equal but an opposite force backward. So when the person says, when I exert a forward force on the sled, you see that the force the person is applying is actually being applied to the sled. So what is the force the sled is applying? What is that force acting on? Anyone? It actually does say it in the picture if you want to read the words.
Is it supposed to be on ground?
There is a force on the ground, but in the case of the forward motion, the guy pulling the sled is applying a forward force on the sled. The sled is applying a backwards force on, it's not the ground, but that is part of it. So you're not wrong. There is definitely a force, action reaction pair for the sled and the ground. But in this case, we're talking about the force the person applies to the sled. The action reaction pair there is the person and the sled. So the person applies a force to the sled applies a force to the person. The force on, exactly, good job, Michael. The force on the person does not come into F equals ma for the sled. We're trying to move the sled with the big rock on it, and F equals ma for the sled with the big rock on it only has F's acting on the sled. So the assistance force on the sled definitely goes on the F in F equals ma, but the force that the sled is exerting, which is the opposite direction, is acting on an entirely different object. It's specifically acting on the guy. So that doesn't matter. That's what's wrong with this. So no, he's not correct. But it's a very common mistake. People sort of think that the action reaction pairs could cancel out, but that's physically impossible. Remember, Newton's second law, our third law, says FAB equals negative FBA. The FAB means the force is acting on A by B. In other words, B is applying a force to A on the left-hand side, but on the right-hand side, A is applying a force to B. So you can never add an action reaction pair together because the two things are acting on different objects. It's like saying, uh, I gave my daughter a push down the hill and my neighbor's kid fell over. Right? It doesn't make any sense because the two forces are acting on entirely different things. Hopefully that helps you with this conceptual example. You can read the answer yourself at your leisure. And the rest of this is really about solving problems. So what I want to do so that you can begin solving problems is I want to explain to you what weight is. I want to derive the formula for weight. So what I'm going to ask you is to consider, you all right, baby? Consider an object of mass m in free fall. Remember, in free fall, which is what we studied sort of in the end of chapter 2, but also the whole vertical motion and projectile motion is acceleration due to gravity with no air resistance. Okay. So what that means is you can imagine you have a ball of mass m and uh, it has no air resistance. So there's no air resistance on it. What we know is Newton's second law of motion says the summation of forces is equal to mass times acceleration. So uh, I'm looking for a very specific word that represents the force that the Earth has on the ball. So this is a ball in free fall, and the Earth is pulling it with a very specific word that starts with W. Can anybody tell me what is the force acting on this ball? Just the word that it's called. You could say a capital G or a lowercase g word if you wanted, but that's not the word I'm looking for. What is the word for the affinity that a planet has for an object? Oh, y'all been this new Windows got me screwed up. Y'all been answering questions all this time. I just found out there's like a little tile with all your little initials on it, and it's got all these little numbers. I'm sorry. The whole time I've been looking at a private conversation with one particular person that sent it to me, thinking that nobody's been replying. The word is weight. So it's W, which equals the weight. So that is, in terms of free fall, that's the very definition of the only force acting on the object. So from Newton's second law, the left-hand side is just W. Okay. But we know that's the only force acting on it. So that takes the place of the sigma F, which means all the forces added up. But since there's only one force acting on it and it's the weight, we just put W there. And it's all in one dimension, which you can sort of picture as the vertical dimension. Maybe down is positive, and we call that the positive Y direction. That would be perfectly fine. Now, the right-hand side of Newton's second law is mass times acceleration. Does anybody know of the specific symbol? Let's see if I can figure out how to see your individual comments instead of just the private conversation. It seems like I can't do it that way. I'm still not figuring it out, but oh well. Nope, I can't see it. I'll have to figure that out before next time because I'm having a hard time seeing. There it is. There's a button called main chat. Now I found it. Gotcha. Yes, gravity is the answer. And there's a specific symbol we use for the gravitational acceleration. Anybody remember what that is? The fact that it's gravity might help you. Gravity. Gravity. It's G. So in free fall, we know the acceleration of the object is actually G downward. So just by setting up Newton's second law of motion for an object in free fall, we were able to derive the formula for weight. So for instance, uh, Mr. Younger's weight is equal to 116 kilograms times 9.80 meters per second every second. And that is equal to 116 times 9.80 gives me 1136.8 newtons. So that's really how you calculate someone's weight is you multiply mass times gravitational acceleration. Of course, if we were on the moon, then it's the weight of Mr. Y on the moon, and that would be 116 kilograms times 1.63. I think I remember that being the uh, acceleration due to gravity on the moon. Yeah, 1.633. So meters per second is equal to 189.5, roughly. Okay. Any questions on that? Now it's technically 750. I will tell you that whenever you have, for instance, this calculator sitting on the table surface, you can tell from Newton's first law of motion that the net external force acting on the system must be zero. But you know there is a force acting on the calculator, and it's called the weight. So what happened to that force? Why is the net force zero? Well, even though that table, which is being represented by my arm, is an inanimate object, it still has the ability to apply forces to things. And in fact, it applies what we call the normal force. And normal is just the appropriate mathematical phrase for a vector that's perpendicular to a surface. So there exists a normal force, and that's the force that holds a thing from going through the surface of a table, or holds a shingle from going through the surface of a roof, and it's always perpendicular to the surface. And that's about the last of what we need to study. I'm going to work some more problems next class time, and I might even work some over the weekend and post some examples from this chapter, but we're essentially done with this chapter. Feel free to ask me any questions you might have on Tuesday. But you guys are free to go. Thanks for coming. Uh, Make sure you sent me your first and last name, and the O01B or asynchronous if you're in that class as well. You're free to go. Have a safe, fun weekend. Make sure you get your test done. You have online test one as well as face-to-face test one. If you're thinking you're not going to be able to get it done by Monday, you might want to go ahead and let me know. Make sure you let me know by like Saturday or maybe Sunday at the latest. There might be some other ways. Also, remember I sent out an email saying that anybody that hadn't done it by Monday, I have an 8 a.m. to 10 a.m. slot available that you could meet me on the Virginia Beach campus and have me proctor it. But you're also allowed to proctor it on your own, as long as you have either two webcams or one webcam that's not attached to your computer, or a webcam that is attached to your computer with a mirror, and then you can take the test on your own without a third party as a proctor. Thanks, everybody. I won't be able to stay as long today, but I will try to wait for the last person to leave. Adriel, did you get my email?
I did get your email.
Okay, sorry about that. I hope you already went back and found it, but I meant to email you last night. I just didn't get to. I found it right just before I left.
I have a quick question real quick.
Yes.
So I have an appointment at like the Norfolk campus to take the test Monday morning. But so to have the papers and stuff, like I'm not gonna have like do I have to show them something so that they know it's okay? Or like they'll already know.
They know that a formula sheet's allowed. I've
Okay.
also sent them an electronic copy so they in principle can print it out and have it there for you. Sorry, I just lost my voice.
No, you're fine.
But you
Okay.
should be able to they should have it, or if you bring your own, they're just going to copy it and send me a scan of it to show that you didn't alter it or make it illegal in any way.
Okay. And then were we allowed to have our calculators or no?
Yes, you are allowed to have your calculator.
Okay, cool beans. That's all I needed. Thank you.
It just can't be one on your cell phone or anything else
Right.
that access the internet.
Okay, cool.
Okay. Thank you, Diana.
Mhm.
Anybody else?
I guess I have a couple of them.
Okay, go for it, Adrian.
You got the email that I talked about with the problem, yeah?
Yeah, I think I got it in a text message, wasn't it? Or did you get it in the maybe it was an email? Yeah, I was thinking it was a text message, but no, it looks like it was an email.
Because I still cannot get it in me for some reason to just do the kinematics because I don't know. I don't think I'm even getting the
Let me check. I'm pulling up my email now. It's confirmed it was definitely not a text message. I was convinced you were wrong, but I was wrong. There it is, Adrian.
because I think it was even some things like trying to eyeball basically the distance in the sums, which I just straight up can't do.
Gotcha. Is this the one that says a person walks in a distance X northward?
Yeah, that was one of the simpler ones that I just couldn't figure out.
Okay.
Because the other one was just figuring out the acceleration given just a simple time range. I think it's just, oh God, if it's calculus related, I just can't do it because I still need to. I haven't even tried to review my calculus. I just couldn't even figure out most of the rest.
Gotcha. Well, the one that I'm looking at right now says a person walks in a distance X northward, turns around, walks a distance 7.00 X southward. If
Yeah.
the total displacement of the person from his starting position is 400 meters, what was the total distance walked? So the total displacement is 400 meters. That means X minus 7X, which is negative 6X, of course. Negative 6X is 400.
Yeah, which I didn't even get. Which I think I got the first time around as basically 566. 500, no, 466 meters. Because I added displacement plus the x.
Right. This should be X should be 33
I didn't even get close to that.
meters, but
I just got x equals 66. Probably only the closest one.
no, it's X. X is 33.3 meters, but what they're asking you is the total distance he walked. So he walked a distance X, which is 33, and then he walked another distance 7X, which is 7 times 33. So that would be a total distance of 8 times 33.
I don't know how you got 33 then because I basically just did 400.
267 should be the right answer. they got 457. What'd they do that for?
Because I did displacement plus the x.
Oh, it's 66. Yeah, you're right. That was it. 66 times 8. So yeah, that's 533 meters is the right answer.
Wait, what?
So let me show you on my notepad.
Yeah, it's just I swore the x was 66.
Yeah,
If that
it did turn out to be 66. I'd made a careless arithmetic error in my head, but you know how that is. So what we're doing here is, let me share the screen again if I can ever get it there. So what we did once that comes up is you can imagine the person was here. Well, actually, I will start it a little further to the.
Yeah, he went up and then went down.
So he went a distance X, and then
Yeah,
he
and
went
then went back.
1, 2, 3, 4, 5, 6, 7. So this is 7.0x. And they said now this distance, which is what we call this distance, which is what we call displacement, is,
Is negative 400. Yeah, I got a similar one.
but this distance is also 6.00x. So 6.00x is equal to 400 meters, means x is equal to 400 meters divided by 6.00, which equals 66.67 meters.
Yeah, I got the first time around thinking I did it wrong.
But they ask you, the question specifically said, I'm pulling it up.
Yeah,
Uh,
which is find the distance. So
no,
what
what
part
is the
of
total?
displacement plus x did not?
What is the total distance walked? And the total distance walked was 8x.
Oh, is it x?
So yeah, that 8 times 66.6666 whatever gives you basically 533 meters.
66 times 2 was 5.
A lot of times you just have to draw it to make some sense of it. Hopefully that drawing helps you a little bit, but if it didn't, then try to figure out some way that your brain can wrap around.
Just because I forgot to double it.
Mm.
Uh, the other, I just can't seem to.
Your volume's coming in and out, so I'm only hearing like every third word. I'm still not hearing you.
Uh, the other times it's just graphs because I just can't figure it out. I
Uh,
think some of them are just eyeball the graph, which I just can't do at all.
do you have a picture of one you can send me?
I can send one over on the email,
That's fine.
but I could just send another one on.
I didn't get one with that. That's the only problem I've gotten from you so far is the one that
Yeah, I know. I'll just fast send another one.
that's cool.
Uh, because I could
Was it something
not
you saw on the practice test or something you saw on the homework?
on the practice test. The homework I haven't even bothered looking since it was finished.
Gotcha.
Basically, yeah.
So I can look on that.
This is the other. I just sent it over in the same kind of line.
Okay.
Yeah, this one I swore just because I just did geometry with some strange numbers because I assumed by graph.
Oh, there, your email finally got here. Okay, here's the graph.
My answer was 38 on that one, just by straight up doing geometry on it
So
and taking the labels.
never assume the graphs are to scale.
Yeah, which is why I keep getting it wrong.
So I'm
Yeah.
drawing this now. This is T in seconds, and this is V in meters per second. And it goes, and this would be 2 right here. This is 2, this is 4.
I'm also gonna ask one more about like immediate givens because one of oh god. Yeah, it's just too many. It's just in this one quiz that I tried to do for chapter 2. It's already like it's already like 3 questions that I have no idea how to solve.
Yeah, that does happen sometimes.
Because 2 of them are graphs with no formula and they just tell you figure out the thing. And then the third one was finding the acceleration with no value to constant acceleration. They just tell you it's constant acceleration. They give you a distance and a time range.
Mm-hmm.
The time range is not 0. It's 1 to 2 seconds.
Gotcha.
Which means I have no clue on how to figure out the velocity.
Right here, find the total distance run by the player in 10 seconds. Okay, so the total distance run by the player in 10 seconds, is that X in meters or is that velocity? Okay, that is velocity. So
Yeah,
in this case,
because I thought it was the curve. No, the area under the
yeah,
graph.
it should be the area under the curve because the derivative of the position as a function of time gives you the velocity as a function of time. So that means the integral of the velocity as a function of time should give you the position. So if you consider that he basically was going 4 meters per second at a maximum, uh, down here, the area under here would be 1/2 base times height, which is going to be 4 meters for that little part. And then for this little part, it's going to be 1/2 of 2 for the width and 2 for
To
the
the
height. And
try.
that's going to give you 2 meters. But then I also have to add 2 by 2. So this gives you 6 meters. And that's all the area under here that I just finished doing. That first one I did was this one. Now the area under the C is going to be that's 4 to 8, so that's 4 wide and just 2 tall. So it's going to be plus 8 meters for part C. This is part B, and this is part A. And then for part D, we get a positive amount right here, which is 1/2. The height is 1, or the width is 1, and the height is 2. So this would be 1.00 meters. But then this one down here would be negative 1/2 of 1 times 2, which equals negative 1.00 meters. So the answer should be 4 meters plus 6 meters plus 8 meters. So that'd be 18 meters. And you said you got that, and that wasn't right, right?
No, I just simply assumed that because I got 38 and then I just divided it by 2.
Gotcha. And did it tell you it was right, the 18 meters?
No,
Because
I'm
it
still
looks right to
trying
me.
because I'm like still so if with trying to figure out even things like average speed, given a position of an object as a function of time, which I swore
Uh-huh.
is once which I swore is once again the area under the curve, but
Gotcha. Yeah, it's the area under the curve for each part.
is it the area under the curve to find speed?
Yeah, but notice part of this area came out to be negative. That was part of the issue. Wait a second. That can't be 18 because they want to know the total distance. Uh, what I did with the positive one and the minus one, that's erroneous because that's the kind of thing I do to figure out displacement. I went a distance of, positive one, but I also went a distance of negative one. In reality, maybe it should have been 20 meters. I think that's the right answer. Yeah, 20 meters because the total distance ran for each of those triangles is one, even though in one case it's one negative, in the other case it's one positive. So I would say the answer is 20. And I'm going to pull that up real quick just to make sure. I know this is from chapter two, so I'm going to open up my chapter two questions, which should be the calculation problems, not the conceptual. I'm pulling that up now to look at it, and I'm going to try to find it.
Is it doing that in relation to zero? I thought you did that in relation to
You thought I did what now?
God, because I covered the whole area under the curve, which included past the origin. Uh, I did the whole thing past y equals 0, so I was just calculating it as if y equals -2 was the bottom ceiling.
Yeah, I just checked it. I'm right. It's 20 meters when you're trying to say the distance traveled. So I was right about that. And I was also right because another question is the same thing, only in that case, they're asking for the total displacement, and the total displacement was 18 meters.
Okay. 2, 4, 2. 2 times. Wait, what? T. Okay, yeah, I see it.
Well, the fact that
Uh,
another way you can think about this, and this sort of goes along with the labs you've been doing, hopefully you've been learning about some of these labs. Do you notice that the slopes of all these lines are basically, or all these line segments are straight lines? That
yeah, but I can't seem to eyeball the. I can't seem to immediately eyeball.
Yeah, but that means the fact that they're straight lines means the acceleration is a constant. So you can actually calculate the average velocity for each of those spans. Like the average velocity on A is just 2 meters per second, and they did that for 2 seconds. So that's 4 meters. The average velocity for B is 4 plus 2 divided by 2. So that's 6 divided by 2 be 3. So that's 3 meters per second. They did for 2 seconds. So now I've got a 6 on that, which is the same thing I got before. So you can do it other ways rather than finding the area under the curve.
Uh, and then just finding the average speed.
Yeah, remember the average when you're dealing with constant acceleration, the average is just the two divided by you add the two together, the final and the initial, and then you divide it by two, and that'll give you the average velocity. So that's why I took 0 plus 4 gives me 4. Then I divide that by two, that gives me 2. 2 meters per second times times 2 seconds is 4 meters. So the path A gave me 4 meters. The path B gave me 6 meters. The path C, that one's a constant 2 meters per second, but we did it for 4 seconds. So that's 8 meters. And then for D, uh, you could say the average is between 2 and -2. And if you add those, you get 0. But that's not very helpful that way. So it'd be better to break it up into D down to V equals 0, and then D from V equals 0 to V equals -2. But the average velocity between 8 and 9 seconds is 2 plus 0 divided by 2 is 1. So that's 1 second times 1 meter per second. So that gives you 1 meter for half of D and 1 meter for the other half of D. So you get 2 meters for the two parts of D. That makes sense?
Yeah. Uh, oh God, because I'm. Oh God. I guess I'm trying to figure out the average speed on another graph because I don't know if it's just figuring out the points in the line or if it's the area under the line. They've given you a position versus time graph, which I just keep. Yeah, I'm just second guessing myself because I think it is speed under time. I think it is the line slope. I don't know.
I just wrote down the right answers for those so you'd know. Did you have any questions about this? It sounds like you're talking about some other problems when the things that you're
Yeah,
saying.
yeah. That the one I showed you. Yeah, I think I got it. Yeah, it was yeah, based on origin.
Gotcha.
I overshot the question. I would just send you one more problem because this one just keeps screwing with me.
Okay. Send it to me. Tell me or read it to me. I might be able to find it myself and you won't even have to send it.
An object starts from rest at time t equals 0 seconds and moves with constant acceleration. The
Okay.
object travels 3 meters from time at 1 second to time at 2 seconds. What is the acceleration of the object? That's the question.
Okay. I'm looking for it right now. Okay, an object starts from rest at a time t equals 0.00 seconds and moves with constant acceleration. The object travels 3 meters from time t equal 1 second to time t equal 2 seconds. Is that the one you're talking about?
Yeah,
Okay.
that
So
one. What is the acceleration?
all right.
This
Stop share here for a second. Let me share again.
one
What
I
we're looking
swore
at
you had
right now, I think this is the problem that you're referring to.
Yeah, 2247. Yeah,
Okay.
2.247. Yeah.
So it says it moves with constant acceleration. The object travels 3 meters from time t equal 1 second to time t equal 2 seconds. They did tell you it's constant acceleration. So the average velocity, notice, remember average velocity is always distance traveled divided by, or average speed is always distance
Oh,
traveled.
it's another kinematic. So
Yeah, so
G
in 1 second means the average velocity is 3 meters per second. And
plus AT. So oh god, you have to find two velocities in that case
yeah, so
because it doesn't start at 0 seconds, so you can't just. Uh,
it's an object starts at rest at time t equals 0.0 seconds and moves with constant acceleration. The object travels 3 meters from time
if
t
it's
equals 1 second.
you could just glean the end velocity because it's 1 second.
Yeah, you can at least find the average velocity between at the end or something like that. But there's a bunch of different ways you could do this. You could say, for instance,
It's just trying to figure out the. I think figure out the initial velocity.
let's see. So we got t equals 0.00 seconds. D equals 0. T equals 1.00 seconds to
Is this like you have to do the what is it, the defined integral to find the initial velocity?
I don't think so. I mean, this doesn't seem like one you have to do for that, but what we're doing here is trying to figure out what the motion is. So we have acceleration equals question mark. So what we know is the velocity, or excuse me, what we know is the position at t equals 2.00 seconds minus the position at t equals 1.00 seconds is equal to 3.00 meters. Uh, and yes, and at x at t equals 0 is equal to 0 seconds. So we have that. We also know a equals a constant. So let's see, t equals 0 seconds, t equals 1 second, t equals 2 seconds. Okay, we got that. So x, since it started from rest and since the acceleration is constant, we know x has to have the form 1/2 a t squared plus 0 plus 0 because v0 equals the initial velocity, but it started from rest. Since it was at rest, we know that. So if we say x equals 1/2 a times 2.00 seconds squared, let's say this quantity minus 1/2 a times 1.
I think the simple one is just trying to figure out how one gets the initial velocity.
Well, that's
Because I
what
think that
no, the initial velocity said the object starts from rest, so the initial velocity is 0.
the initial velocity starts from rest and
So
moves at constant acceleration.
now what we can
But
do,
then just try to find the velocity at 1 second. That's the
but do you see what
problem.
I wrote here? I wrote x of 2 seconds.
It still shows the question. It still shows the bank.
Oh, gotcha. Sorry. I thought I shared it already. Yeah, I guess I didn't share with the right thing. Here you go. Let's do this now. So this is going to pop up in a second, and it'll make some sense when you see it. So if you look right,
Oh, you use the 1/2 AT.
yeah, but you see this part right here?
Oh yeah, xt minus 2 sec. Oh, xt 2 seconds.
Yeah, for x of 2 seconds minus x of 1 second equal to 3 meters. And since the acceleration was a constant and the initial velocity was 0, the equation is basically that x equals 1/2 a t squared plus v0 t plus x0. I just put all that in there. Now I've got from this, I managed to get this equation.
Uh,
I can multiply both sides by 2, and then I'd have a times 4.00 seconds squared minus a times 1.00 seconds squared is equal to 6 meters. And then all I have to do is factor out the a. This would be 4.00 seconds squared minus 1.00 seconds squared, 6 meters. So A is equal to 6
6
meters.
divided by 3. So
Mhm.
2. Oh,
So 2.0 meters per second per second.
oh my God.
And that is the right.
I that I think that would break me. Just you just did 1/2 a 2 second squared
Mhm.
minus 1/2 a 1 second squared.
There's no other
Like what?
choice. When the acceleration is a constant, the x turns out to be 1/2 at squared plus the initial velocity times time plus the initial position. So
So
that,
you could just swap those. You could just basically replace the 1/2 second.
mhm.
The initial and yeah, the initial velocity and position were just given, so you could just cancel them out on the fly.
Yep.
Okay.
All right. Feel free to send me any more. I got to go ahead and split. I haven't had any supper, so
Yeah,
uh,
I just have to I just have to get in my mindset on the basically the equation you got before you start doing the math.
Hmm.
because I don't think I would have been able to remember the what
Yeah,
is it, the 1/2 a t squared minus 1/2 a t squared.
yeah. Well, I was just using part of 1/2 AT squared plus V zero T plus X zero,
Is
but
that a thing you could just do? Where you could just swap two instances?
yeah, because they gave us two instances. They told us between t equals 1 second and t equals 2 seconds, the distance was 3 meters.
And that's mathematically correct.
Right.
I don't know how that's the case. Oh no, you're finding the average velocity. No, average acceleration. Oh, wait, what?
You're actually, in this case, they told you it was constant acceleration, so you just knew automatically that the equation x equals 1/2 at squared plus v zero t plus x zero automatically applies. Anytime you have constant acceleration, that is a equation for x as a function of time.
Okay. Okay, yeah. Okay, got it.
Okay. So I knew it had that form, and since they told us it started at rest, and even if it had the x zero not being zero, the x zero was irrelevant to the whole problem. So you might as well call it zero. So that's why I just allowed myself to put a zero in here and here for this.
And then you just did, and then you just basically copied the 1/2 at squared on the same side,
Mhm.
which I don't know, that's the part that confused me because I thought you couldn't do that.
Well, remember it said at t between t equals 2 seconds and t equals 1 second, the algorithm
Yeah.
is 3 meters, and this is one-dimensional motion because it's chapter two. So going 3 meters meant it went from x equals something to x equals something plus three. So I could have written, you know, x zero plus three, but I'd have an x zero on the left as well. All I knew is that the x of 2 seconds minus the x of 1 second had to be 3 meters. And that allowed me to then plug in this part of x for that, and then this part of x for that. And that's what that is, and that is.
Uh, oh, you just copied. Okay, you just changed the you just swapped the x into 1/2 at. Okay, yeah, I see it now.
X is your coordinate.
It's another one of those calculus related things where you have to set the x, right?
Not so much a calculus thing, but you might have seen it first in calculus so that I could understand it.
Yeah, the where you have to define variables, simplify the variables into it, and then you just
Mhm.
uh, that's gonna get me every time.
Well, the good news is there's a finite number of problems, and the fact that you keep working these problems and ultimately finally getting an answer means there's a good chance when you get on the test, you might actually see one whose answer you just remember. So just keep working problems and you might luck out. And then over time, it'll become more than memorization. It'll become hopefully learning and understanding.
I hope so. The online tests we could do basically before the face to face.
I would recommend you doing it, yes, before the face to face.
Okay, because when you said you could proctor yourself, I thought that was the material that you used.
Oh, gotcha.
Okay.
No,
That's not it, but that's not it.
yeah, but
Okay, thank God.
should do the online test beforehand, but at least do the two practice tests beforehand.
The online test is the one you proctor yourself, right?
There's no proctor at all. Free open notes, open book, open internet, but the face,
Okay, yeah, the one and thing.
yeah.
Yeah, okay. I had to make sure because I was scared if I did that online test that was in the module, it was going to be for
No,
keepsies without not open notes, those kinds of things.
no, and not only that, with the online test, you're also allowed multiple attempts. So usually I give you at least three attempts and I only take your highest.
Okay, got it.
Okay.
Yeah, because I haven't even done any of the extra credit so far. Extra credit problems.
Gotcha.
Just been so iffed with this. I've been so iffed with the first two chapters. I think I'll be fine with the third one. I think I'll be fine with the third one because I've been too exposed with vectors at this point.
Gotcha. All right. Well, I'm going to go ahead and split. Feel free to send me by text or email any other questions you might have. Text would be a little easier. I can get them.
Oh yeah, I completely forgot. What is Lab 3 possible at this time? Like, is it possible by
No,
this Monday?
no,
Okay.
no.
So it's
I
being
gave
pushed back
everybody
another.
to I gave you at
So
least
Lab 3 is being pushed back another week, but Lab 4 is due this Monday.
assuming nothing's going wrong with it, there's no reason for Lab 4 to go back. So yeah,
I also. Oh yeah, this. Oh wait. Okay, yeah, I was okay. There it is. I was about to say with Chapter 3, there was a weird mismatch with the parts 1 and 2. Like
hmm
the part 2 was due earlier than part 1, but I
yeah.
think yeah, it looks like it's fixed. Yeah.
All right.
Okay. Yeah. Thank you.
No
I'll
problem.
try to get it sorted. I'll see you probably Monday
Well,
at noon.
remember to text me or email me if you have any problems. I'll be around.
Yeah. Oh yeah, I have to send that email for
Yeah,
the.
I will be gone out of town for the weekend, but I'll be paying attention to my emails and text messages too. So have a good weekend, Adrian.
Okay. Thank you.
Holler if you need anything. Bye bye.